Okay, apparently this is not doing what I want. There we go. Okay, cool. Oops, sorry, Tooks. Hey folks, we're gonna talk about cross-validation today. So let's dive in. Sorry, I can't help myself. So cross-validation. So first let's start with some data. Hopefully some of you are familiar with Hopefully some of you are familiar with one of the best classic shows on the planet. It's almost okay if you're not. I'm kidding, mostly. But anyway, we're going to play around with some data from The Office. So I've already scraped this up for us all. So you're welcome to download it from the GitHub. Here I've got a tibble of ratings of shows from The Office from A Tidy Tuesday. This is a tibble of every single episode with 6 columns of useful stuff, including the IMDb rating, total votes, air date, title, episode, season, for all 188. So here's a nice distribution of the IMDb ratings. They range considerably from, well, 6.5 up to 10, with a nice little histogram here, fairly straightforward. I've got the code on the side so that you can check it out. But yeah, let's crawl into this data a little more, and I'll tell you why, obviously, soon. But we can see here that there is a relationship between the total number of votes and the IMDb rating. It's not exactly linear, it's got a kind of a swooping up, but clearly some of the most popular episodes in terms of votes seem to be associated with higher rankings. And these are broken down by season. As you can see, the season bar is continuous, which is not great, but lighter colors equal later seasons, darker colors equal earlier seasons. So here I've got a GG highlight, which is a cool thing that you might enjoy using. It might be helpful to you, where you can highlight specific episode names and label them. Here we've got the dinner party episode, Goodbye Michael, Stress Relief, and the finale. All of these scored more than 4,000 votes. And I definitely would recommend checking out there's a cool Rolling Stones article about the dinner party episode. But my point that I'm trying to make here is that you can look at outliers and summon them from your graph without having to like grab them from the raw data, which is nice, I think. So let's look a little deeper, and we see here we've got some ratings with box plots, which are overlaid by jitter to give you a better sense of the spread of the data, and then we've plotted them as a function of, we've color coded them as well as plotted them by season. So there's a lot of information happening here. And for those of you familiar with the show, these shouldn't surprise you. The widespread of season 7, the variability increased across seasons. So let's dive a little into modeling this stuff. So I've set a seed so that when we split this data between our training and test sample, we can get that again. So you'll be able to replicate my results entirely. And so here, the initial split, it's broken down. We're just using the default. It's 3/4 by default. And we're going to save the training data as Office Train. And we can see here that 141 episodes have been captured in the training set and almost 50 in the test set. We're going to specify our model, just a basic linear regression, just as a refresher of how tidy models work. And we don't have anything in it right now. So But let's start by actually building a recipe, which is fairly helpful, I find, for doing any kind of cross validation of any, or we'll get to bootstrapping soon. And so here's our nice basic recipe code. We're going to predict IMDb ratings as a function of everything. Now, we're not going to use title because it's not helpful. So we're going to chain that into an ID role, and we'll extract month out of air dates and effectively make dummy variables by month. And also we're going to just cut out everything that doesn't have any variability. All right, so got a recipe now. So effectively we have 4 predictors and 1 outcome. Okay, does this seem straightforward? I realize you can't answer me because first of all, I'm a fish, and second of all, this is asynchronous. But, all right, so we are building our workflow here. So we want to pipe in our recipe into our model into the workflow and just kind of automate this process as much as possible. All right, so here we fit our data using the Office training set and have tossed it through our workflow. And let's spit out our output just so we can see what's happening. Here is the optimal model, apparently. So let's evaluate it. All right, so we are going to make some predictions based on our training data first. So let's use the predict function, plop in our training data set. We are only working with the training data set right now. We don't want to touch the test data. We want to keep that separate. It's in a locked box in Panama with a lot of other papers. We want to keep that isolated so that we can test our final model. So here we're going to look at the predictions of from our trained data that we trained on our training data. So this is going to be our optimal fit. It is designed to capture and estimate it as best as possible. And we're also going to just smush everything together. So here we have a table with our predicted IMDb rating, our actual IMDb rating, as well as our titles, so we can have some sense of what's going on. And you'll notice that these aren't perfect by any means. The Alliance is spot on, but the pilot is estimated to be way better in terms of ratings than it actually was. And Hot Girl, which is an episode I hate so much. I hate this episode. I think it is, I hate it. Part of the reason I think I hate it is because it's like really uncomfortable, which is what The Office. But anyway, so that episode is also predicted to be better. Now let's see how much of the variability we can explain. How good is R squared? Okay, so in this model, we've explained half, more than half. We've explained 53% of the variability in our model, which is pretty good. I would be pretty happy with it. That's effectively a multiple R of like 0.7-ish, 8-ish. It's good. As you'll probably have figured out, models with high R squared are preferable to low R squared because we want to explain more of the outcome as a function of all the predictors. Now, an alternative is the root mean squared error. Now, there are other versions of this, but frankly, this one I think is the most intuitive as like an introduction to how to think about this. So we have our RMSE, which is not the same as RMSEA, but we are trying to find the minimal average distance, or we're trying to minimize the difference between our outcome and predictor, or our predicted value and our actual value. Now here, our RMSE is 0.35. Is that good? Is that bad? I will leave that as an exercise to you. Do we want higher RMSE or lower RMSE? All right. So again, I'm going to leave this as an exercise for the reader or viewer, you. And have you asked yourself, is this RMSE good or bad? Is it low or high? Well, let's actually extract it and see. Well, so based on our ratings, we would, you know what, I'm just going to leave this as an exercise to you. Feel free to shoot me an email or hit me up in the discussion post if this is unclear and you want more info. So, but here's the big takeaway. So what? Who cares about how good our predictions are in the training data? We've literally fit this model to hell and back. It has been optimized to explain the most variance in our data. But so what? Of course it's going to do well because, ladies and gentlemen, it's supposed to. It's designed, it's been optimized. But we want to know if it can work outside our data. So let's see how good it does on our testing data, which is aptly named. We want to see if it is still good at predicting the data, our holdout data. So that 25%. Does our model work well? Because it doesn't know anything about this data. It has not watched The Office for seasons and seasons and seasons over and over again because it is a glorious piece of art. Let's see how good it does. Well, the RMSE is higher and the R-squared is lower, as I've illustrated here. So while the R-squared is pretty good, it's pretty close. The RMSEA is much lower in comparison. But remember, and I'm going to keep saying RMSEA because I'm a structure equation modeling gal, but the RMSE is still in the units that we were looking at. So it's in the IMDb points. So while here the numbers are pretty close, kind of by design, these RMSEs could be way bigger. Say we were talking in dollar amounts, and we're trying to predict GDP. If we are within 50 cents of GDP, that's freaking amazing. So you have to use context for the RMSE. Okay, so the key takeaways that I want you to have here is the training set does not have the capacity to be a good arbiter of performance. It can't tell us how good our data is because we used it to make our model. It is optimized. It is supposed to be good. That is why we are training it. And frankly, it's not an independent piece of information. Predicting the training set can only reflect what the model knows. It doesn't know that the Hot Girl episode is incredibly it doesn't know that. It doesn't know that I have strong opinions. It doesn't know what The Office is. It doesn't. So suppose you, just to give you some sense of here, suppose you give a class a test and then give them the answers and then provide the same test. The student scores on test 2 are not going to accurately reflect what they know about the subject. Those scores are going to be way higher because they have all the information, all of it. And so instead, we need to test them on other data to see if it's not just a fluke of the test or the fluke of the data. We want to see if it's real, if it's legit, if it holds up.